Hi, my name is Matt Bemis. I do technical support for Autodesk for the CFD product, and today we'll be efficiently analyzing electronics in Autodesk CFD.
Hi everyone, good morning. This is Amal. I'm a technical support specialist of Autodesk CFD, and I'm based in Munich, Germany. So, what do we have today, Matt? Just for your information, regarding the link that you see below, you will get like all the documents, like the files that you used, and also the PowerPoint presentation, and this link after the webinar. You can go ahead, Matt.
Yep. Amal, do you want to do poll question?
Yeah, cool. Let's start a poll question for you so we can have an idea about what are your biggest challenges in modeling electronics in CFD. So here we go. So can you please select one of these options, like your biggest challenges in modeling electronics? If it's geometry, CAD cleanup, assumptions, material settings, or the model setup. So we will give you a few seconds to vote. I see that the trend goes most to assumptions and material settings. And this is good right now because this is what we are going to present for this first part of the webinar. So I'm going ahead to stop the poll questions now, and so that we can see the results. So we have here 50% for the assumptions and material settings or material settings, and in the second rank we have the model setup, and at the last rank is the geometry or the CAD cleanup. So I will hand you with the following slide, Matt.
Sure. All right, so here's kind of a step through of today's discussion. This is a two-part webinar series, so the first part is really going to focus starting with a basic CAD model and getting it into CFD and assigning the correct materials, making the right assumptions, and so on. So we're going to start right with a basic CAD model that we actually got on GrabCAD, and we're just going to identify critical parts and try to explain what you need to keep and model in CFD and what you can disregard and how to simplify geometry.
And for the second part regarding the materials and settings, we're going through some of the materials that we have in our database, which are the internal fan, heatsink, the PCB, the thermoelectric components, and finally the compact thermal model. We're going through the material editor and see the different parameters that we have to take into consideration when defining these materials.
All right.
All right. So.
All right. So starting with a CAD model you may be given, or maybe you built yourself, you really have to ask yourself, what are the significant components here? Basically, what matters, and what can I get rid of? So electronics boards have an enormous amount of parts and components that are way too fine to just dump into CFD. So you have to understand, where are the massive heat loads, where is the inlet and outlets, where does airflow come from, and what can you get rid of. It helps to take sort of a macroscopic view and say, what's my end goal here? Am I trying to simulate maybe fan failure, or just doing a steady state analysis, or do I want to know the hottest area of my board, or maybe I have some kind of design constraint that specifies that.
Yeah, or
And
even when you're, I can add like, for example, if you're developing a component and you want to just concentrate on this component, like to see the temperature profile on it or the air recirculation just next to it. This depends, and you have to know these this end goal of the simulation before moving forward to modeling the different components of your model.
right. I mean, we have this little graphic in the bottom right-hand corner, which is what we ended up modeling. And you could argue that you could break this up into many different complete separate parts in model in CFD, or you can take, a whole, board inside a box and see what happens there.
Exactly.
So this is our CAD model. We just kind of identified some critical components here. We have one really large heat sink. We've got a bunch of different chips, a lot of capacitors, and there's a lot of
ports.
Yep, a lot of ports and pins, things that don't have any heat load, but maybe just obstruct flow.
Mm-hmm.
And of course the PCB too.
Like components that they are not very important, like the green ones, they are not very important to the analysis, like they are used to plug in other components, external components, but in here we're gonna like make some assumption for simplification also for them, that they wouldn't like be the most important components of our model.
Exactly.
Mm-hmm.
In terms of how to simplify geometry, pretty much every single electronics board is going to have a capacitor. So this is a great example of how we need to simplify this. On the left we have the before, on the right we have after. The before model has fillets, different actual volumes, really way too many complicated parts. There's actually the two terminals on the bottom there too, which we don't need because they're going to go into the PCB board anyway. So basically we just want to replace it with a complete cylinder and go from there.
Actually, Matt, here we use the SimStudio tools, like we use the feature of remove features. I wanted also to ask our attendees if they use for the geometry simplification SimStudio tools or other software. Can we pull this question so we can know if we have a lot of people like using this feature of SimStudio tools?
Yeah, absolutely. Let's do it.
Okay, let's do it. So can you please answer to this question if you use SimStudio tools for the geometry simplification of your model or other software? So some more few seconds, and we can share the results. So here for the results, we have 50% of attendees who are using other software, using SimStudio, and others, they are rather using other software. And this is good because mostly here we're going to talk about the simplification we made in SimStudio tools. So what have you done for the other components, Matt?
Right. And just a heads up in case anybody is unaware, SimStudio tools is just installed automatically when you install CFD or another Autodesk simulation product. It's super useful for the support specialists because we know it's there, so we can jump on anyone's machine, and we know we can start looking at CAD there. And it also has a bunch of built-in functionality to simplify geometry.
Absolutely.
So, moving forward,
guys, this is Marwan. I just want to mention something here that maybe not. I'm also with the technical support. Sometimes, you might get the model from someone else, and you can actually export the model into a SAT format from CFD if you want to, and open that and say SimStudio Tools or any other CAD package. So CFD gives you the option to export as a CAD format, just in case if you need that. If you got the CFD model from someone else and you don't have the original CAD models files.
Yeah,
Sure.
absolutely.
Thanks for bringing this, Marwan.
Yeah. A lot of times, I might find it when I'm doing support, I might find it being necessary to modify CAD. So I just export from CFD, save as a SAT file, open it up as SimStudio Tools, and go from there. So we are quite familiar with it. So that's what we decided to use here. On the screen, we just have simplifying chips. Generally, there's way too much detail in these integrated circuit chips. We don't need any of the pins. I'd really just rather have it be a rectangle. We're just going to put a heat generation boundary condition on it. So a rectangle or a box is fine, and we definitely don't need the serial numbers on top.
Yeah, for sure.
So here we modeled a fan that was on the CAD model. Basically, I wanted to get rid of the actual blades and replace it with volume so I can use the internal fan material in CFD. So it's really useful to know ahead of time what kind of assumptions you're going to make and what you want, what your end goal is really here. I know, technically I could use a rotating region and, model the fan blade, but there's no need to do that. Most of the time you'll have specifications, you'll have a fan curve, and you'll be able to replace the fan that's on the CAD model with an internal fan material. So all that is on the right is a single volume, and you're going to identify the inlet and outlet faces and attach either a constant flow rate or a fan curve and go from there. Now you'll notice on the right, I actually split it into two volumes. The bus of this blade, which is the center, is very, very large. And so I think it would be more accurate to suppress the center there and have no flow rate and only have the outer ring volume be the internal fan material. Both are considered valid. It's just what you think would be more appropriate for the simulation. I simplify the heatsink as well. One of the questions you have to ask yourself right off the bat is, can I basically afford to mesh the heat sinks and model them as is, or should I replace them with the heatsink material? The heatsink material is used when you know your element count is going to get way too big. Basically, it replaces the heatsink, the physical heatsink that we see in this image with a box, and you identify basically a flow-through direction and use cross-sectional area parameters of the fins to get an approximate cooling and heat transfer capacity, and basically that'll allow you to have a much smaller element count, get simulations done faster, and all. In this model, we're not too worried about element count, and there's only one heatsink, so I'm just going to assign it to be aluminum and then mesh it. But before I do that, you will notice I got rid of a ton of fillets. Of course, got rid of the fasteners. There's no need to model those, and the tabs that hold the fastener. So I definitely got rid of quite a bit of details here, but still, of course, keep the overall shape. So this is just sort of a before and after. We replaced a ton of the ports and a ton of the pin boards basically with boxes. SimStudio Tools has a great feature called replace with primitives, And basically, you can grab a component and it'll put a box around it and use the externalmost dimensions. So you can see this is done basically around the perimeter of the board. We just replaced with oversized blocks that we'll later on just suppress and not even mesh.
Okay, so I think before going deep into the materials and setting, do you suggest that we ask the question about if our attendees use the electronic analysis, to use it in to have the end goal simulation of simulating a passive cooling or a forced cooling using a fan?
Yeah, absolutely. We can go ahead and do that. Basically, we just want to know, do you model forced convection stuff, natural convection? What are you modeling with electronics? Go ahead, Amal.
Mm-hmm. So in here, we want to know which type of electronic analysis do you usually model? Is it the forced cooling using the fan or the passive cooling? That means the natural convection. And this way we can have an idea about the most used simulation in electronics. So, more few seconds.
I didn't expect a tie. We need somebody to break the tie right now.
Okay, so let's share the results. It's 50-50.
So, yeah, I think going forward, we're going to end up actually picking one of those and implementing it.
Yeah, for the second part.
I guess it'll be up to our choice which one we want to do, which is fine.
Yeah, it's okay.
All right, so moving forward, now that we kind of showed you how to do some CAD prep, we're going to look at the materials and in settings and really show you how to define these once you're into CFD. Capacitors and chips I actually just lumped into one because basically all you're going to do is mesh the volume and then apply a heat generation to it. So all that's going to do is take the total heat generation in watts and uniformly apply it over the volume you have there. So that's exactly how you want to model chips or capacitors. Super straightforward.
Yeah, the easiest component in here.
That's why I picked
Yeah.
to do it. All right, so next we have an internal fan. So the internal fan is a tiny bit more complicated, but still quite easy. Basically, you grab a volume, select the face to get a flow-through direction, and at that point you can just hit OK. You can use a constant flow rate, or you can decide, I need to use a fan curve. Basically, I find a lot of users implementing fan curves when they don't even need to. So a great approach is to run the model with a constant flow rate, which you think will be characteristic. Maybe grab a middle point in the fan curve, run it, and then look at your pressure delta and see if you're even operating on a curve. It works fine, but it does introduce complications, and it just is easier to use a constant value if you can get away with it. The rotational speed, basically, it's an optional parameter, but if you have it, it certainly helps to apply it. Basically, it applies a rotational component to the velocity exiting the internal fan, so it's just not normal to the exit face. So this will especially be important if you want to capture the higher turbulence basically on ships on the downflow section of the internal fan. The slip factor is an inefficiency. It's used to describe the velocity at the end of the blade tip of the air compared to the velocity of the blade. So in a perfect world, it would be equal to 1, because at the end of the blade, the air would have the exact same speed. But this is just an inefficiency. It's fine to just use a default value of 0.3. You could use 1 too, but it's a fine detail that doesn't have to doesn't have to be introduced unless you want it to. So
This is
right
interesting.
now, yeah. So right now, I'm going to jump into a CFD model I did with an internal fan. Just give me 1 second. There we go. Sorry for the delay. All right. So here's a simple model I made in CFD. I just want to show you how to use the internal fan and how it works, basically that. So in the middle of the screen, I have 3 large air volumes. I'll go ahead and hide them. Basically, it's just a tube of air. At this face, over on the right side of the screen, I actually have a surface resistance. Basically, I wanted really low pressure on one side of the fan to show you how the fan curve operates and how it works. For boundary conditions, I just have 0 pressure on each end, 0 pressure gauge. Very straightforward. Basically, air is going to come in one side, go through the contact resistance, go through the fan, and then we'll see if the fan is operating on the curve like it should be. So these are my results. Now you'll see this is on the downflow side, basically the outlet. You'll see there's a higher velocity around the perimeter, and that's because we have that rotational speed specified. It's instead of directing a flow that's just normal to the outlet, basically this face, it's actually going to have a higher velocity on the outside, just like a fan blade would, which is great to see. And I'll show you pressure in a Y. All right. So here, basically after the resistance, we have a super low temperature. Super low pressure, or in the negative compared to atmosphere pressure, and so we know there's a pressure delta there, and we may be operating on the fan curve. So if we look at the summary file, we will get data for internal fans. So here we have the name of the fan, which is just one of the default ones. And here's the operating pressure rise. So this is a number we want to keep in mind, and go look at our fan curve and our operating flow rate and see if things are working like they should. So we have 0.05 inches of water and almost 26 cubic feet per minute. So what I'll do here is jump in here. All right, so 0.05. All right, so we're going to be between points 4 and 5 on the fan curve, and like we said, so that's 0.05 inches of water, so that works out well. We had about 25 cubic feet per minute, which falls in between these 2 points. So everything is working like it should, which is great news. One other comment about the meshing is you want to use a uniform mesh on the internal fan components. Pretty straightforward. That doesn't look uniform to me. So that could have been my mistake, but it's considered a best practice to use a uniform mesh just on the internal fan component.
Yeah, and even more than like 4 to 5 mesh elements from the inlet to the outlet.
In the flow-through direction?
Yeah, exactly.
Yeah, I actually am too short here too, so
it's okay.
Did this a little too fast, but 4 to 5 elements in the flow-through direction from inlet to outlet is best practice here. So
thanks.
Let me go back to the PowerPoint. Just give me 1 second. All right. So now we're back. So now going past internal fan. All right. So all right. So next we have the heatsink. Like I spoke about earlier, we're just going to mesh the aluminum instead of using the heatsink material. Basically, I know we can get away with the element count here. It's not a big deal. I'd rather just model it as is. It's easier, and you don't have to make any questionable assumptions. So this is aluminum. We don't really have to worry about the mesh on the aluminum too much inside the metal because we're just looking at conduction here. Any electronics modeling, the temperature range is so small that we're not going to see variable properties in the aluminum. So you can keep the aluminum as fixed material properties. This mesh on it is fine. It could be coarser. It's not the end of the world. What is important is that you want a decent mesh in between the fins. So you absolutely have to have a midpoint there, and the more elements, the better. I would say at least 3 in between the fins is necessary. There's a lot of different tricks you can use to get a better quality mesh inside the fins. I've seen people break the area in between the fins into separate volumes so they can apply refined meshes there, or you could use refinement regions in CFD. So there's a couple different tricks there and how to do that. So next is applying the material setting for the PCB. You have a couple different options here. In CFD, you could actually grab one of the many default PCB boards under solids, which have a standard 12-layer, and you can base orientation to get your conductivity right. If you want to make your own PCB material, it's absolutely fine, and we have a whole section of materials for that. And basically, there's 3 total parameters that you're going to edit in order to get your PCB physical properties correct. You have your total PCB thickness, which is just what it sounds like, and then you have traces and planes to fill out, and then define a dielectric material. Basically, how this works is your total PCB thickness is your biggest number in terms of height. Then when you go into traces and planes, you define a material for the traces. Generally, this is copper. It could be something else, I guess. And then you use this table on the right to define how many different layers of traces and planes there are. and what percent metal, percent volume is metal. So you can see here the first plane has a thickness of 0.5 millimeters and is 35% copper, and so on. Now, basically, this when you sum this table, it sums to 4 millimeters, and you know your total PCB thickness is 10 millimeters, so that excess 6 millimeters is actually the dielectric material, which is just the insulator. Now, as you change these components, over on the left, your effective normal conductivity, effective planar conductivity, density, and specific heat are all going to change. And basically, you can play with these settings and edit what you need to in order to get overall accurate characteristics. Here's just a little schematic. It's actually from the help documentation, and it just helps kind of show you the different layers. On top, we have the top trace, with its percent copper and thickness, just to get conductivity, and then you have your dielectric layers, and so on. So most of the time, the dielectric material is FR4, but it can be changed to really anything you want. Anyway, now we're on to thermoelectric component. So Amal, can I hand the presentation to you?
Yeah, sure.
All right.
I will take it. So, hope you can see my screen.
I can see it.
Okay, so thanks, Matt, for explaining how to set the other components up. Now we're going to talk about two more materials, which are first the thermoelectric component. So the thermoelectric component, or the electric cooler device, it's also known as a Peltier module. And its role is to move heat away from critical components to keep them cool, and vice versa. Actually, the Peltier effect creates a temperature difference by transferring heat between two electrical surfaces. So when the current flows through the junctions, as you can see from the scheme, so when the current move in this way, it carry on like the heat from these junction. So heat is removed from this surface and is carried on this surface. So it's so that's why we get this temperature difference between both of the surfaces. So this surface is kept cool and this is heated. And I want to hand you with some helpful tips for the modeling. The thermoelectric component cannot contact a compact thermal model material. It's the kind of material that we're going to explain in the next slide. And if you want, in case you want to use it, you can just define, if, for example, you have a chip, two resistor chip, you can just model it as a solid and then put a thermoelectric component over it, for example. But it's not possible to model both of them above each others. And for the thermoelectric component, the way to model it is it's just a cuboid, a simple model, as Matt explained for the chips. And we can the parts contacting the hot and the cold sides of the tech device must be meshed. We can't have a part contacting one side or two sides of the tech device that is suppressed, which is not meshed. We should really make sure to mesh all the parts contacting the hot and cold sides of the tech material. So we're going now to move to talk about the different parameters of the material editor of the thermoelectric components. As a first step, we would define the geometry of the tech material. So we have here the units, which was the units that we want, and the G, it's the geometry factor, which is the ratio of a pin cross-sectional area to the couple hay. Just to remind you that the thermoelectric component is like a box, and inside it there is a lot of pins which are conducting the current inside this component. Oops. So what we have to define in this section is the number of these pins, which are named as couples, and the ratio of the geometry of the pin cross-sectional area to the couple hay. For the next step, it's to define the control method. So this defines the mode of operation of the tech device. The default choice is T-cold. Wherever, for example, if you want to use the simple default material we offer on our library, you're going to notice that the control method by default, it's T-cold, which defines the tech device to have a cooling effect with a target cold temperature. For the parameters we have the T-cold, as I already mentioned, the T-hot. If you want that a target temperature is to be hot, that means that you want to have your tech device add heat to the user-defined tech surface to maintain the temperature. So in this case, your tech or the control method of your tech is like working as a heating device. Or if you have rather information about the voltage or the current or the power, so you can just use them in your material editor. It's like when you're not interested in controlling temperature on some components next to the tech material, but rather on controlling the current or the voltage of your tech material. And the other sections are defining the material parameter coefficients, which are the Seebeck coefficient, the electrical resistivity, and the conductivity. Actually, these values are temperature dependent and are defined with polynomials. The coefficients and the simple devices are a good starting point, but check with the tech manufacturer for coefficients values for specific devices as needed, because sometimes it's good way to use these coefficients as a starting point, but after that, if you got like information or data from your manufacturer, you have just to put them in this section. So I made a sample modeling or simulation of the tech material, and I represented two ways to do it. It's on the left side. You see that here I defined. I wanted to maintain the temperature of this solid, or I named it PCB, like cold. And on the right side, I wanted to maintain rather the heat sink or this aluminum solid as cold. So for the left side picture, I defined T-cold on the bottom side of the thermoelectric component. And in here, I just choose a temperature like 60 degrees on this bottom side, like to maintain the PCB hot and like to keep the heat sink cold. So let's move now to the compact thermal model. So the compact thermal model material in Autodesk CFD, it's a resistor compact thermal model. So it consists of just 3 nodes: the junction and the case and the board. It's just 3 nodes. The junction is also referred to as the die or the chip. The case is the top surface on the package, as you can see here, and is where a heatsink may be mounted to the package. The board node is a single, it's in here, like here, a single point of contact between the board and the package. The nodes are connected by thermal resistance between the case and the junction, so this is the RGC, and the resistance between the junction and the board, and this is the RGB. In the 2 resistor compact model, heat transfer is only computed at 3 nodes, which are the case, the junction, and the board. The sides of a 2 resistor compact model, or the CTM, it's easier to say it, are considered adiabatic. Only the case and the board sides allow heat transfer to their surroundings. The case and the board sides of the device are isothermal and are modeled with a high conductivity in the in-plane direction. So when you're modeling your CTM, you're gonna see that the heat goes in this direction only, and you're not going to see a change in temperature on the side walls of your CTM. Some helpful tips for the modeling of your CTM are the following. So it must contact a part that is assigned to a fluid material. You have to make sure that you have this condition, and it must contact one and only one PCB, or you will get like an error message saying that you have more than a PCB or a solid with a PCB in its name, and it cannot contact a PCB material that is suppressed. If you have a PCB material next to it which is suppressed, an error will be issued and the solution will not run. And let's move to the material editor. So here we have only 2 parameters to define in the CTM model on the material editor. So we have the theta JC and the theta B, which are the resistances between the different nodes. These values for the resistances can often be obtained from the component manufacturer's specifications. We have like a simple CTM in our library database of the materials, but you can use your data that your manufacturer provided for you for this for the CTM. Probably you're gonna ask yourself, at which time should I model my chip as a CTM, and at which time should I just model it as a solid? I would say this depends on your end goal simulation. If you are interested, especially on this model, like to see the temperature gradient on this component, I would say use the CTM. If you are rather interested in seeing like the global heat transfer inside the whole model, and you're not interested in this part or this component, you can just model it as a solid, and then affect like heat, the total heat generation as boundary condition. Yeah, actually the total heat generation boundary condition, you can use it either when applying a CTM or a solid. But this depends, after all, on your end goal. I think we are already done with the materials and settings, and we would like now to know if you have questions regarding some of the points of the presentation we already presented.
So Amal, there's quite a few questions here. There's one asking about the, all right, so on the capacitor, there's two lines on the top of the simplified capacitor. Maybe you want to go back and show that, Amal, maybe not.
Yeah, okay. So, on the presentation.
Yep.
Yeah.
Yeah, really we were just having a hard time prepping or getting our CAD right and getting those lines away. I was struggling to delete those, so that's still something I have to work out. That's all. There's no significance there.
Yeah. So we can see it from the whole model that we have here. It's already simplified.
Yeah, we were able to.
We got rid of these lines.
Yeah, it was a pain, but just took some messing around.
Yeah, exactly.
Someone was asking about the heatsink materials and how do you account for the surface area loss. So basically, Amal, maybe it'd be better if I shared my screen and looked at the material editor for heatsinks.
Yeah, sure. So you can show it. So I'm gonna make you the presenter.
Sure. All right. So here I just opened the heatsink material editor. You're basically specifying a base thickness, base conductivity and fin conductivity, which are usually going to be the same, and then the type. So the thickness, and here, let me jump out of here. And you first specify the approach and base surface. The approach surface is just going to be the flow-through direction. It's going to automatically put basically an outlet on the side of the volume. So when you use the heatsink material, you don't want to apply it to what in CFD is an actual heatsink. You want to apply it to a box, just a standard box. And you identify the approach surface, and then you identify the base surface, basically to tell the program where the heat transfer is going to occur and where the conduction is going to occur. So base thickness is straightforward enough, so is conductivity. And the type, you have to choose. You have to choose between the variation. So you could do microchannel, pin fit in line, pin fit staggered, offset strip, heatsink profile. So there's these are all just the standard heatsink configurations, and you'll notice as you run through them, there's a little schematic to show the spacing and identifies the parameters which you have to input. So, and there's some good help documentation online. Let me pull one of the pages up. One second.
Yeah, on the help documentation talking about how to model the heatsink.
Yeah, this is just a public article. I just Googled heatsink material Autodesk CFD, and you have more explanation on the kind of heatsink. I mean, this is a microchannel.
Yeah, a lot of many types of them.
Right. So this will help explain. It's super useful, and that's that. They will take into account, the pressure drop basically on the flow through. So, like I said, you don't want to go in here and apply a heatsink material to our heatsink. You want to replace this volume with a box and then do it on that. So.
Sure. So let's see the other questions. Okay, I'm just looking where we did stop. So we have here, could you suggest to set up resistance material which could be used, for example, to simulate the filter? Filters are very common in electronics. Yeah, I agree. It is always hard to find conversions with resistance material in the model. Do you have any suggestion how to make conversions smooth? Actually, for the resistance material, first it depends if you are using surface resistance or volume resistance. For the volume resistance, you have to make sure that you have like 4 to 5 mesh elements from the inlet to the outlet. And with the uniform mesh, you have to make sure that you're using advection scheme 5. And for the conversions, actually it depends, because we can't be 100% sure that the conversions is like affected, especially by this material or by other factors in your model. So probably it would be a cool idea, like to model a simple box with volume resistance inside it, and see if you can get like a smooth curve of conversions.
Right. And just a follow-up there, if you for some reason have a notoriously hard time using resistances, maybe the move there would be to just do a run with it as air. Just don't include the resistance at first, just to confirm that your convergence plot looks good, and you can get a converged model, then go back and add it. I like the approach of building up. And I think the tough thing with defining resistances is not using them, but getting data on how they behave in terms of pressure drop. I would probably start with a free air ratio, because that's the simplest, and go from there.
Yeah, exactly. Like to go to the difficult settings, like defining a head capacity curve or something like this. It's starting simple.
So there's a great question about extending inlets and outlets. You really want to do that to make sure there isn't any recirculation. You saw in my model of the internal fan, you know, on the upstream side, basically on the inlet side, you definitely want to extend quite far. I mean, maybe just 2 diameters or so, but you just want to get it away from the internal fan material. You don't want to make this more complicated than it needs to be. Just get it away from the internal fan a little bit. And I mean, on the outlets, go ahead, Amal.
Yeah, actually, Matt, we can do it for the second part of the webinar, like to simulate the forced convection analysis, because here we have a forced convection because we have the fan, and we can walk through the steps of defining the openings, extending the inlet, outlet, how much should we do it, so that we can give more details on this area.
Sure. I absolutely agree.
This is a good point.
Yep. Yeah, we can go over that in the second part.
Okay, so and there is a question. It may want to be pointed out that a PWB defined by a material can only be used in an orthogonal orientation within the model. If you have a slanted angle PWB to the coordinate system, you should use a PWB part so the PWB normal can be defined. This is a good point, actually. Yeah, actually, it's a good idea that we didn't think about to mention. Thanks for sharing this. Do you have other questions, Matt, on your side?
No, I think the point about orientation is just that by default, these parts are kind of stuck on a Cartesian coordinate system. So you can modify conductivity in X, Y, or Z, but not really a function of something in between, which I've heard people, voice their opinion about. I mean, it's in most applications, Cartesian, being offset by 90 degrees is good enough, but if it comes up, it can be a huge pain for sure. But I think that's it for me, Amal.
Yeah, I think we're good now.
All right. Well, thanks for attending. On part 2, we're going to implement all these old materials, run some simulations, and show you guys some results.
Yeah, the whole actually it's like it's gonna be like a good idea as one of the NTD mentioned to mention the setup, like how we ended defining all the model and the settings of the solver, and we can go also through the conversions part and to the post processing of the results. I hope that you're gonna enjoy this. Regarding the files and the PowerPoint presentation, you will get it under the link that you can see in the first page of the PowerPoint presentation. After when this webinar ended, we're gonna put everything in there. Thank you very much, and we wish you a nice day.
Awesome. Thank you.